Okay, so I'm going to say something about the solution theory of linear constant coefficient difference equations. And the motivation for studying this is that oftentimes one can think of multi-step methods as linear difference equations. So let's set up the framework for this. So let's say that we have V, and let this denote the set of all infinite sequences of complex numbers. So let's say x is x1, x2, and so on, and y is y1, y2, and so on. Okay, so on this set, then we're going to define, it's like a few basic operations. We're going to define sort of addition and scalar multiplication. Okay, so if you're going to take x plus y, as you might imagine, the way you define this is by adding terms component-wise, right? So that's x1 plus y1, x2 plus y2, and so on. Okay, and then scalar multiplication, lambda of x is just the component-wise multiplication by the scalar. So it's lambda x1, lambda x2, and so on. Okay, all right. Then obviously the zero element of this with respect to the addition operation is just the infinite sequence of all zeros. Okay, and so this endows this space V with a vector space structure. Okay, so space V has a vector space structure. And when you have vector spaces, you can talk about basis functions or basis vectors, and the basis, one possible choice of basis is just the following. So V1 is say 1, 0, and so on. V2 is 0, 1, 0, and so on. So sort of the obvious thing, it's like, so the basis just consists of vectors, it's like which is 1 at one point and 0 elsewhere. Okay. All right, so once you have that, then you can try to write down, if you will, difference equations, constant coefficient difference equations, in terms of operators on this vector space V. Okay, so let's see how you go about doing this. All right, so the fundamental operator, it's like on this vector space, is what's called the shift operator. Shift operator. Let's just denote this by E as a map from the vector space to itself. Okay, and then E of x is just going to be basically what happens when you drop the first term in the sequence and then you just push everything to the left. So that's x2, x3, and so on. Okay, and you can look at what's happening component-wise. For each component, it's like of this infinite sequence. So if you shift x and you look at the nth component of that, that's really just the nth plus first component of the original sequence x. Okay, So once you have this shift operator, then you can write down linear difference equations in terms of a linear difference operator. Okay, so let's consider a linear difference operator with constant coefficients. And finite rank. Okay, so the general form of that is the following. All right, so let's denote that operator by L. It's a linear combination. I'm going from I equals 0 to m of Ci e to the ith power. Okay, and it's understood here, that when you take e to the 0th power, this is nothing more than the identity. Okay, and then more generally, what you have is that when you take ej of x, right, and then you look at the nth component of this, this is nothing more than x n plus j. Okay. All right. So this is a linear difference operator, and you can imagine interpreting this as being a polynomial, if you will, in this shift operator. Okay. So L is a polynomial in the shift operator E, okay, which we denote by the following. We say that L is some polynomial in the shift operator E, okay, where P is the characteristic polynomial. If you will, and it's given by just P of lambda is equal to the sum of Ci. Lambda I goes from 0 to m. Okay, so by now it's like you might be seeing that there are some similarities between the theory of linear constant coefficient difference equations and linear constant coefficient differential equations. So it's very, very natural then to ask, it's like what the general solution theory is for these things. So let's see how you go about doing this. So I want to determine all solutions to an equation of the form L of this vector x is equal to 0, and since L is a linear operator, right, solutions satisfy the principle of superposition. And as a consequence, they form a linear subspace of V. So how do I go about doing this? So at this point, it's perhaps helpful to think back about what you do when you're encountering a similar problem with sort of linear constant coefficient differential equations, right? So in the case of differential equations, L might be some linear combination of the derivative operator, and then you're trying to solve L of y is equal to 0. Okay, and if you recall, it's like the way you get at the characteristic equation for a linear constant coefficient differential equation is you substitute y is equal to e to the lambda t. So you might ask perhaps what is special about y equals to e to the lambda t. And the main observation is that y equals e to the lambda t is the eigenfunction associated with the time derivative operator. So what I mean by that, if you take the time derivative of e to the lambda t, you'll see that it's lambda e to the lambda t. Okay, so in the context of linear algebra, this is analogous to saying that if you have a matrix A acting on vector x, this is equal to lambda times x, right? So this is the usual eigenvalue, eigenvector combination. And then now it's like instead of having a matrix, you have a linear operator acting on a function, and this function is the eigenfunction of that linear operator, in the sense that when the linear operator acts on that eigenfunction, you get lambda, which is the eigenvalue, times the eigenfunction itself. Okay, so that's sort of what is distinguished about y e to the lambda t, and you can ask, is there something similar which happens with difference equations? Okay, so now the indifference equations, right? The basic object which you're working with is the shift operator. We have the shift operator. And so it's natural to ask, it's like if you take the shift operator and you think of it as essentially an infinite dimensional matrix acting on an infinite dimensional vector, what the associated eigenvector to the shift operator is. Okay, so if you have E, it's acting on vector x, right? When is this equal to lambda times x? Okay, so this is the eigen, it's like value problem. Okay, so you can write this in terms of components as before. So if you look at e of x and the nth component of that, okay, you know that is equal to, by definition, just x, the n plus first component of x, but it's equal to lambda x. So this is equal to lambda xn. Okay, so now you have a recurrence relationship which tells you it's like what the sequence of x have to satisfy. Okay, so one possible choice of an eigenvector associated with this problem is v, which looks like the following: lambda to the 0, lambda 1, lambda 2, and so on. Okay, so I've been quite sort of selective, it's like in terms of how I've done this. The reason why I've chosen to write the first term as lambda to the 0 is to deal with the case where the eigenvalue is 0. Okay, so if the eigenvalue is 0, that's saying Ex is equal to the 0 vector. And so you might ask, well, what is the non-trivial term associated with that? So the simplest non-trivial eigenvector of the 0 eigenvalue is when you have some constant in the first term and zeros in the other term. So if you write it in this way, then 0 to the 0 is 1, and so that includes the case for lambda equals to 0. Okay, so in any case, that's the vector, if you will, associated with the shift operator. And then once you know that, then the same way that if you solve when you take this ansatz e to the lambda t and you substitute it into this linear operator equation and get the characteristic polynomial, finding the roots of the characteristic polynomial give you it's like the basis for the solutions. The same thing happens with the linear constant coefficient difference equations, which are homogeneous. So let's write down the theorem. Okay, so the theorem is as follows, right? So if P is a polynomial with a root lambda, right, then V equals to lambda 0, lambda 1, and so on, is a solution of this linear linear constant coefficient difference equation, Pe acting on, let's call that x, I guess, equals to 0. All right. And then if all the roots of P are distinct, then each solution of the difference equation is a linear combination of such special solutions. Okay. All right. So so this is relatively easy to prove. Okay. So again, let x be lambda 0, lambda 1, and so on. Okay. And if you take the shift operator on u and the nth on x and the nth component of this, right? This is of course xn plus 1. Okay. And in this case, that's lambda to the nth power. And of course, this is just nothing more than lambda times lambda to the n minus first power, which is lambda xn. Okay, so this is basically telling you that E of x is equal to lambda of x. So x is a eigenvector, it's like of the shift operator with eigenvalue lambda. Okay, so then, right, P of E acting on x, okay, is equal to, so I'm going to define, I'm just going to expand what P is. Okay, so it's the sum from I equals to 0 to m of Ci e to the I acting on x. Okay, and then you can check that this distributes in the usual way. So this is going to be the sum of Ci lambda to the I of x because of this shift property which we derived just now. So I equals to 0 to m. Okay, and then this is of course nothing more than p lambda applied to x. Okay, And since we assumed it's like from the get-go that lambda is a root of this characteristic polynomial, then this is equal to 0. Okay. All right. So basically, the solution theory is relatively straightforward. If you have one of these linear constant coefficient difference equations, you basically look at the corresponding characteristic polynomial, and then you find the roots of this. If the roots are distinct, then the solution space is spanned by these infinite sequences of the form lambda 0 to lambda 1 and so on, where lambda is the root of the characteristic polynomial, the roots of the characteristic polynomial. So one final situation remains, which is, well, what happens if you have repeated roots? Okay, so let's talk about that. And then again, I'm going to try to appeal, it's like by analogy, to what happens in the linear differential equation case. Okay, so in the case of repeated roots, so you might recall that in the case of repeated roots, for the sort of differential equation case, instead of just having e to the lambda t, you have t e to the lambda t, t squared e to the lambda t, and so on. Okay, and then how many of these terms you take depends on how the multiplicity of the root. Okay, so for difference equations, what do you do? Okay, so you have this eigenvector, if you will, of the form lambda 0, lambda 1, and so on. So one way to sort of see where these things come from is that you differentiate the original e to the lambda t with respect to lambda, which is the eigenvalue. Okay, so if you differentiate e to the lambda t, you get t e to the lambda t, and then so on. Okay, up to constants, which don't matter so much. So you do something similar. So you take v, it's like, and you differentiate with respect to v, with respect to lambda. Okay, so you get 0. So lambda to the 0, right? 2 lambda, 3 lambda squared, and so on. And you keep doing this basically, right? So you keep differentiating this eigenvector, if you will. It's like with respect to lambda, the appropriate number of times to get the sort of basis for the solution space you're working with. Okay, so you can keep going. So in any case, this tells you something about you know, what the solution theory is. It's like for linear constant coefficient homogeneous difference equations, and what again what the basis for the solution spaces are. So let me just stop here.